Welcome back. So we're going to finish up plane waves tonight, taking the plane waves and bouncing them off walls in various ways. And the last time we were doing it was finally interesting in a generalized symmetry, so we were off to the side throwing it on a bank shot, if you want to think about it that way. So non-zero angle of incidence would be the more formal way of saying that. And we're going to start with a perfect conductor. The wave comes in at an angle of incidence, and it's always true. It's true that an angle of incidence will equal the angle of reflection. That's one of the fundamental laws of reflection, and that comes about from a conservation of momentum. And so you can, in fact, show the components equaling out in a vector decomposition. The idea of momentum is kind of an interesting one. It comes from a velocity and a direction of propagation. So speed and a direction of propagation. And where those lie, if you think about physically about a plane wave, where those lie is in k. Right? K tells you from the dispersion relationship has the speed of the plane wave in the particular material. That's from the dispersion relation because it has the epsilon in it. And it also E crossed with H happens to lie for simple materials in the direction of K. And so K is a harbinger or a carrier of the momentum of the wave. And you can say, well, gee, you need mass to have momentum, and the only maybe exception to that is unless you're moving at the speed of light. And then maybe the mass becomes sort of a singularity that you can fudge around, and that's exactly the case with photons. Photons have no mass, but they move at the speed of light, and so in fact, if you take h bar, the fundamental constant of quantum mechanics, and that's Planck's constant divided by 2 pi, and you multiply it by k, you'll get a quantity that has units of momentum, and in fact it is momentum. Now, for us to have direction in it, we had to generalize a little bit. Every time we've talked about a plane wave, we've had it going in one direction, along one axis. That's a remarkably trivial situation that's not going to happen too much in real life. You can pick your axis once. Remember, the wave doesn't care about your choice of coordinate systems or your units of measure or anything like that. It doesn't even know you're there. And so if you have one wave, yeah, you might be able to pick your axis of propagation so that it lines up. But as soon as you bounce off of a mirror at an arbitrary angle, that doesn't hold anymore. Right? Or as soon as you refract through a prism, that doesn't hold anymore. And so in general, this e to the ikz is a real trivialization of what's going on. And it's not that big a jump then to say, as we did last time, and this is a really kind of important thought here, is k is going to go to a vector k, and so this term kz is just one term of a dot product. So if r is equal to x times a sub x plus y times a sub y times c times a to z, then kx times a sub x plus ky times a sub y plus kz times a k sub z dotted with that r is going to give you three distinct terms. Okay, and so that's a very important generalization, and I like to think about it in the context of momentum. Certainly, that's borrowing a little bit from the quantum mechanics, but it's not a big leap. Okay. Now, the problem that comes up here is subtly difficult. It's such a broken symmetry that we really have to consider Ex, Ey, and Ez. Think about this. My z-axis is in this direction, and so my electric field can point in any direction in x, y, and z. Okay, and so it's not because the direction is written propagation is written quite generally with respect to the coordinate system. So is the expansion. So is the field expansion, the vector field expansion. And so I really have to consider the EX, the EY, and the EZ terms. Okay? And then similarly, I have to consider the corresponding HX, HY, and HZ terms. Okay? So I've got in total 6 terms of my fields to really track down. And what we do for bookkeeping, and also because it helps us with the boundary conditions, what we do is we consider 2 cases. We consider the case we started to call 3A last time, and this is commonly called the transverse electric condition, the transverse electric condition. So we picked that the electric field is pointing in one direction, and it's pointing so that it's tangential to the plane, to the XY plane. And so in this case, it's going to point definitely in the X direction. Now, if you think about that, the H component is going to lie perpendicular to it and perpendicular to the direction of propagation. And so it's going to have 2 components. It's going to have a component that's projected in the Z direction, and it's going to have a component that's projected in the Y direction. See, this line here creates a triangle where the 2 legs are in the Z and the Y direction. Okay? So this transverse electric field for this geometry that we've considered gives us the E sub X component, the H sub Z component, and the H sub Y component, which, if you're counting, is exactly half of our problem. It's exactly half of the work we have to do. And so you can imagine that we're going to come up with a case 3B, and that case will be the transverse magnetic component. Okay? And so I like to, we use these we use these TE and these TM designations quite a bit, and we forget a little bit about what their job is. And their job is really to make the boundary conditions upon reflection manageable. But in general, you don't really have a TE or a TM wave. If you force a TE wave, or you force a TM wave, that's all well and good until you break symmetry again. Okay? So I was involved in a project a few years ago where we had a waveguide that supported a TM wave. We designed it rigorously, but then we bounced it off of a 45-degree mirror embedded inside the semiconductor. So the mirror had a dimension of about 100 nanometers by a couple microns. Small mirror, trust me. Interesting to make that mirror, but we did. And so even though we were TM with respect to the walls of the waveguide, because of the slash of a 45-degree cut in it, we didn't have a TM wave relative to that new surface. And I'll tell you, it caused a tremendous amount of confusion in group meetings while we were working through all that stuff. But wait a minute, it's TM. No, it's TM with respect to the walls of the waveguide, not with respect to that. And so my preachiness here is just to remind you that, don't assume you have TE or TM. Just assume you have 6 components of fields that you have to keep track of. Okay? And make sure that you have all of them accounted for. Okay? And it's not that, and if you think about it that way, then it becomes less confusing. It becomes maybe a touch more work, but the work you're taking on is work that you would have ignored and gotten wrong on a project anyway. So it's kind of good work to do. Okay? All right. So enough of that. I just want to set the stage for that, because usually if you go back and you look at your notes, you'll be so tempted to say, oh, is this a TE case or a TM case, and divide the two sharply. But remember, the spirit of superposition of plane waves is that you want to find a simple solution, another simple solution, and use superposition to build up to something that's more realistic. Okay? And so that's exactly the case here with TE and TM. All right. Now I know a lot of you have a fair amount of experience in the microwave regime, and you might be scratching your head at this, but if you go back and you think about it, your TE or your TM designations are always with respect to one one plane of reflection. And as soon as you have an interesting problem of many planes, then things change to be a little bit more sophisticated. Okay, and I bet if you go back and you look at all the times you assumed it, you had a real you never broke symmetry on that, or if you did, you probably got something wrong. Just a thought. Okay. All right. So last time we assumed an incident and he reflected, and the way we looked at this problem was kind of interesting. We lined up first the k, the momentum vector. Then we lined up E, and then we said, okay, where is H? It's perpendicular to it. So you actually have to go ahead and do this right-hand rule to figure out where H is. Hang on, I want to make sure that I. Okay, good. Now, the incident electric field points in the x direction, and it has some magnitude, and it's propagating e to the ik. Now, our dot product introduces angles, right? It introduces projection angles, exactly how the dot product is supposed to do. And the projection angles in the y is a sine theta, opposite over hypotenuse, and in the z direction, adjacent over hypotenuse, it gives me the cosine term. Okay, so if I breathe one in or breathe one out, they work symmetrically, right? They go against each other. And if you look carefully at the if you look carefully at where the projections are, the wave that's going on input is going against what I called the z-axis originally, and so there's a minus sign in there. Okay, so minus of minus is a plus, and that's the shift into the minus direction. Okay, so that minus sign there comes about from the fact that the projection is a minus k cosine theta. Okay, on reflection, that flips sign, because that projection is moving up in line with the z-axis. Okay, so the red component here, or the y direction of k, sees the reflection of the surface. It sees the surface, it sees the reflection, it flips sign, it goes from moving against z to moving in positive z in reflection. And that's handled in this plus and this minus and this plus sign here. Okay? Now it's interesting to also look carefully at what's going on in the y direction for k. Okay, that's the blue vector that I have there, and that's moving parallel to the metal. That's moving parallel to the metal. So that's not going to, in fact, see the surface. And in fact, it doesn't. There's no change upon reflection to the y component of k. It just goes back and forth. The analogy is you're sailing. And I always like to think of myself as sailing somewhere off the eastern coast of Spain, but you're sailing on that north tack, past Barcelona, and if you just sail parallel to the coast, you're not going to encounter the coast. You're not going to be able to make landfall. You're not going to go into the nice bars and restaurants that Barcelona has. On the other hand, if you are going if you're going perpendicular to it, you will encounter the boundary, and you will encounter all the boundary conditions that has to offer. So I look at this wave, and we just wrote it down, right, from the way the picture looked. But I look at this wave distinctly as two different elements: one that's going to go ashore, and one that's just going to sail parallel to the shore. Okay. So very, very different. And in fact, if you orient the incident angle so that it's normal incidence, all your wave hits the shore. If you turn it so that it's 90 degrees, even beyond what the term is grazing angle, then it sails right by the metal surface and doesn't interact with it. Okay. And then you have to mess with a little bit of the infinite nature of the plane wave, but that's not really germane on this. Okay, because you will in fact have a surfing of things going on there. Okay. Anyway, the boundary condition then acts. ER is equal to E minus of EI. That's to make sure that there's no charge inside the material and no field inside the material. So just a squidgen inside negative Z, there is no electric field. So that means that the electric field has to cancel itself totally at this point here. And when I substitute all that into y equals 0 and z equals 0 into this equation, I get ER is equal to E to minus EI. Okay? So what that means, and that's sort of, then we're able to substitute in, and we're able to get a little bit of a simplification. And as I was pointing out with my little travelogue to Spain, I have a traveling wave that's moving in the y direction, and now a standing wave that's moving in the z direction. Okay, so I have a situation that looks like that. All right. I want to digress a little bit. I don't digress enough in this class, and I think it's the camera that inhibits me a little bit, and I apologize for that because I enjoy the digressions, even if you don't. There's another situation of superposition. If there's a plane wave that's coming down this way here. Now, supposing there's also a plane wave that's coming back down this direction here. Okay. In this case, I have two reflected waves that come back out, but I have a balance against the traveling wave in the y direction. Okay, and so I have a wave, because I have a second wave, that I can create a superposition right along this y-axis. Okay, and that superposition can be seen in several ways. Supposing I start with one laser and I split it up into two, so they're perfectly coherent plane waves, and I send one down this line here and one down this line here, then where their beams overlap on the surface, I'm going to get a standing wave pattern. High, low, high, low, high, low. And in between, in the nulls, I'll have no field. On the peaks, I'll have a lot of field. So now if I smear a photoresist, some photoemulsion on it, or a photoresist on it, then what I'll have places where there's light, and the photoresist gets activated, and then I'll have places where it's dark, and the photoresist does not get exposed. So then I can process it, and I can wash away the activated side, and I'll have a plus minus plus minus. I'll have a grading right along the surface of that, and that's a commonly used technique to create what they call holographic gratings, just in terms of simple superpositions. And so if I come in with two beams, I get a nice striation line grading pattern. If I come in with three beams, so let's say it's 180 degrees, so it's 60 degrees relative to each other, the lines become triangles, which become hexagons. Okay, which becomes hexagons. And so I can create. If you've ever made soup over a burner, sometimes you'll see the hexagon patterns, right? So the hexagons come up a lot in problems of nature, and this is another example of that. Well, an interesting application of that hologram is you wash away the photoresist, and then you put it in an oven just to soften the sides, the hard edges of that hexagon, and they droop down into little lenses, little curved domes that can act as little micro lenses. Okay. Now, there's a much better way that we came up with for creating micro lenses, and that was just to use an inkjet printer to splat plastic against the glass surface, photoresist against the glass surface, and create a nice, like a snowball against a window. Oh, that doesn't hold in Texas. We barely get snow, but you can imagine that happening. Okay, sorry. All right. Anyway, so these are some of the areas where these kinds of problems can come into play. And we'll talk about others. For example, the wave that flows inside of a waveguide with two metal surfaces like this, and the wave bounces off and is guided by the reflections on the metal surfaces. Okay, so we'll talk a little bit about that probably in lectures to come. Okay, all right. So now we have made great strides to solving this problem, but we're still a little ways out, right? We know where the wave is going to go. We know something about how the total electric field is, but we don't. And we know we've even found this minus sign here. Okay, so we've got to put this minus sign into the problem. Okay, so let me use a new picture for that. This is my reflected wave, theta reflected, or just theta in fact. And the electric field coming in was pointing in the positive, which direction did I label that? X direction, right? It's pointing in the positive X direction. So now upon reflection, where does it point? Well, it points down. It points in the minus X direction. Okay? The H direction, the H field is looking like that. And so I have to figure out where my H field is pointing. And if I do the right-hand rule on it, to kind of find that out, I have it coming up this way. And so from there you can discern exactly where the H is what the components of the H are doing. The H is going to have pointing in the minus Y direction and the minus Y direction here. It points in the positive Z direction here, and it points in the negative Z direction there. Okay, so that simple little right-hand rule. E, knowing that E is perpendicular to H is perpendicular to K or S, that's borne out here. Okay. So now we'll do case 3b, and here we have the magnetic field that's transverse. And again, all we're doing is we've clicked off what happens to three out of the 6 terms. So if this E, a simple picture of E, begets 2 terms in H, then a simple alignment of H will get us the last 2 terms of E. See how that works? So EX, it will give us HY and HY and HC. We'll pick now H sub X and look at the boundary condition for H, and the E will be more complicated. So let me draw my there's my Z-axis, there's my Y-axis, and there's my X-axis coming out of the page. My K is sitting there. I want to consider H aligned up with the X direction, that's tangential to the plane. Transverse magnetic, tangential magnetic. It's kind of a funny word. I much prefer the pictures rather than trying to remember what the T stands for in TE and TM. Just personal case. I was never much on terminology. The mathematics and the picture and the physical meaning are much, much, much more germane and easy to read. Otherwise, the vocabulary is just memorization. But people use it so commonly that we have to pay it its due. All right, so here's H incident, and H incident will point in the x direction. And we'll go ahead and write down what H incident is. It's very similar to what we had for E incident before. So H incident is equal to H incident prime, some amplitude times e to the minus ik times y sine theta, and that's this projection here, minus z cosine theta, which is the projection of k down into the z direction. Take a quick look at that, and I'll flip back to the electric field that we had. E to the minus ik, y sine theta minus z cosine theta. Here it is exactly the way we had it before. Okay? So we're not thinking too hard when we're writing this down. We've done some of this case before. Okay? H reflected. Looks like that. And I write that down simply because I know what k is doing, and k is the only information that I need for that exponent. Now, when we did the normal incidence case, let's see if I can find that. Normal incidence. Oh, I didn't bring that. I'm sorry. If we remember the normal incidence case from the from the electric field and from the magnetic field, the electric field flipped its direction. There was current on the surface, but the current and the electric field flip acted so that the magnetic field was preserved across the boundary upon reflection. Okay? So, as before, H reflected prime is going to equal H incident prime. There's no minus sign there. Okay? And it's exactly the same case that we did before. If I remembered the other notebook, I would have brought it, and you would have seen that. It's in your notebook, so flip back to it. And again, I have one component of the H field that is acting normal to the surface, reflecting normal to the surface, and from there, and the other one doesn't see the surface, and so it's an identical case of what we had before. So I know exactly where H is pointing, and that's pointing up in the x direction. I can add these two guys together and I can get an H total. And because I don't have the sign flip, SIGN flip, the sign, I have a cosine here for my standing wave on my z-axis. Okay. Now we have enough information to worry about where the electric field is doing. Again, if I I have to find the E cross H that gives me the K. So I have to twist my arm here a little bit around. And you see that lining up the right-hand rule in the K direction and sweeping towards the H direction means that my electric field points up into this direction. And that electric field there has a projection in the Y direction, and it has a projection in the Z direction. So, if you're with me on the bookkeeping, we pick the H sub x, and quite naturally the electric field has a Y component and a Z component. Okay? So I'll just go ahead and label this as the TM case, and this case as the TE case, just for grins. Okay? Okay, so now on reflection here I can play the same game, and I've got to line up my right-hand thumb with K and do the right-hand rule, and I see where my electric field reflected is. Okay. And that's really all we need to figure out what the electric field is. Because the electric field is going to have two components. The incident is going to be eta sine theta times HI. So that's the component that's lying in the Z direction. So I have the sine theta projection from away, and then I have this eta term which changes units for me. Moves me from my E to my H to my E. Okay. And if I look back here, I see that I have the same thing going on with my reflected wave. The component here is the same component here. And so I can write down E reflected in the Z direction is also equal to eta sine theta H. Reflected, but it's really the same as H incident, right? The Y component will have the eta in it. It will have the cosine projected part of H in that direction. And it's pointing in the positive Y direction on incident. Oh, but look, upon reflection, it's pointing back in the negative. So there's a sign flip from the boundary conditions on the Y component. Okay. So that right-hand rule saves us a lot of thinking. If you're willing to contort your hand and maybe sprain your elbow, you save yourself a lot of algebra. It's usually a good sacrifice. And that's going to be minus eta cosine of theta. And we can write it as H sub r, but it's really also H sub I. Okay? Because they're the same. And again, we can go ahead and write the total. And there's two. think that's a minus sign. Double check me on that. And again, I can play my trick of separating out the standing wave. And similarly, I have that. I skipped a couple of steps. You agree with this minus sign? Okay. So, in general, again, you have the TE case and you have the TM case. Many people will keep those compartmentalized. All the textbooks dutifully run down one and run down the other. And I'll just add, again, that the real world is a hodgepodge of both of those, a superposition of both of those. Okay? And you'll be lucky if you, and oftentimes you will, but you should acknowledge your luck when you have the symmetry that you only have to consider one or the other. Okay? All right. Now, the last case to do with reflection will be an arbitrary angle of incidence on a dielectric. Okay, and it's a nice problem to work out, and it's kind of beautiful, but it's also kind of a lot. It's a lot of math, and there's not a lot more insight into it. And so what I'll just do is I'll just give you the equations for it, and you know, you should probably plot it or take a look at it a little bit just to acknowledge the symmetry of it. That's how it's pretty much how you're going to be using it anyway. So in a dielectric, in addition to an incident and a reflected angle, you're also going to have an angle that's transmitted inside of it, and that angle is found by Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. N is the index of refraction. That's how we all memorize it. And N is related to epsilon. Usually it's basically the square root of epsilon, but I'm being sloppy and kind of an engineer about that. And so, again, you break your problem up into a TE case and a TM case. And you can define reflection coefficients and transmission coefficients exactly like we did before. The reflection coefficient for the TE case is ER over EI. And for the transmitted case, it's CT over EI. The etas are the impedances of the material. You can also write this in terms of epsilons. You can also write it in terms of the indices of refraction. But we've been using etas, so it makes sense to do that. That's how we generally characterize one material from another. Eta 2 cosine theta incident minus eta 1 cosine theta tangential is in the numerator for the reflected coefficient. Notice that if theta goes to 0, I'm measuring from the normal as I always do, then I have eta 2 minus eta 1 over eta 2 plus eta 1. Exactly what we had before. But now I have additional cosine factors in throughout my, to degrade or downgrade the component of what's actually being reflected. Okay? The transmission also looks similar. If I get rid of the cosines, I have 2 eta 2 over eta 2 plus eta 2 plus eta 1. And then I downgrade these by additional cosines to account for the fact that not all of the wave is bouncing off the surface. For the TM case, I have reflection coefficients and transmission coefficients as well. They reduce down to the same if my angle of incidence is normal. Eta 2 minus eta 1 over eta 2 plus eta 1. 2 eta 2 over eta 2 plus eta 1 again. If you just do that, you say, well, what's different about it? And then you start looking at the subscripts on the angles. So here's cosine of tangential in front of right behind the eta 2. Up here it was right behind the eta 1. And then the angle of incidence is now behind the eta 1, where it used to be behind the eta 2. So very subtle kind of a change there. And similarly in the denominator, I have the same reversal of the cosines. Okay? So a little bit of broken symmetry on that, and you can think a little bit about why that has to be there. Okay? All right. Okay. Well, let's say so long to plane waves. Not really, but we'll pretend we are. And we'll move off into transmission lines. Okay? And we're going to approach transmission lines in a very non-electromagnetic way. Okay? So we're actually going to get away for a little while from Maxwell's equations. Okay? But they're buried in there. Okay? We're just going to treat it in a slightly different manner. Now, I call this lecture Waves in a Long Thin Circuit. And to emphasize that, I'll have a transmitter and I'll have a receiver and I'll have two lines that link those guys together. Okay? So I'll have a wire 1 and I'll have a wire 2. Now, whenever I say long, that's sort of a qualitative word, right? But what do I mean when I say long? What do I mean long with respect to? A wavelength. Always a wavelength. Okay? So, what that means is if I have a wire and I'm working at a small frequency, 60 hertz, 100 kilohertz, and I've got a wire that's about this long, the voltage across that wire is exactly the same. Right? The voltage along that wire is exactly the same. However, if I now decrease my wavelength to say 10 gigahertz, so the wavelength is smaller than that wire, I can set up a situation where I can pump voltage and current across that wire. I'll need a return probably, but I can shove power transfer down that wire. But if I freeze time, the voltage here will not necessarily be the same or equilibrated to here. Okay. So this is circuit. It's a little bit of a circuit theory problem, but it's not, because I am celebrating, in fact, the fact that I can have many wavelengths, many cycles of voltage change or current change in these wires. Okay. Now, you know that a length of wire has an inductance. You probably calculated that in your undergraduate or maybe even your high school physics class, right? And it doesn't even matter because we've been working with inductances all semester. Mu, as long as we have a material, even vacuum has an inductance, right? So when I say that there's an inductance associated with this line, yeah, okay, you expect that. And same with the capacitance. If I've got two wires spreading apart, or whether they're flat or planar or what have you, yeah, there's going to be a capacitance between the two. Okay, and because they're wires, they could also be losses, resistors. Okay. Now, to get this into a situation where I can apply circuit theory, I'm going to consider a very small piece of this transmission line. Okay? And if I pick a piece that's small with respect to a wavelength. Okay, so if I'm a tenth or a 1/100th of a wavelength, I don't really have that much change across the wavelength. So if I pick my DZ small enough, then even though the whole transmission line is out of circuit theory, within this little red box, I might be able to get away with circuit theory. Okay. So in this case, I'm going to pick an inductance per unit length. And I'm going to pick a capacitance per unit length. And eventually I'm going to pick a resistor in there, resistances as well, losses per unit length. But for now, I think we'll be doing well just to get in the inductance and the capacitance. Okay? So I'm going to have two points on my input and 2 points on my output. So I'm going to have wire 1 and I'll have wire 2. I'll go ahead and draw the second wire. Okay. And this length here is my discretized length DZ. By the way, if I make DZ too big, so that there's a sizable voltage across this, then I have to divide my DZ by 2 or by 4 or by 8 until it works. Okay. The construction that we'll come to will be okay, but we'll have to, to start with, we just have to make it small. And by the way, if you're modeling this in SPICE, for example, or modeling it on a discrete time case, then yeah, you have to worry about DZ getting small. All right. Now, there's an inductance per length. There's an inductance per length, and that goes along with the wire. Okay, and I think if you do the work for a 1 inch, piece of wire, it's about, I think it works out to be about 8 nanohenries per inch. Does that number sound right to anybody? You probably don't work with inches anymore. You probably work with millimeters. But that's roughly speaking just the basic inductance of a wire. Okay, so there's some inductance there, just for the fact that there's current flowing down the wire. And so we'll represent that as an inductance per length. So the total amount of this inductance is L times DZ. And I'll call that total value L prime for that inductance. So L has units of henries per meter, and henries per meter multiplied by meter is going to be equal to L prime, or henries. Now, on the input of this, is going to be a voltage. And this voltage, if you look at this, this is occurring at some point Z. The beginning of that little red block is located at some point on the transmission line Z. So this voltage on the input of that block is a voltage as a function of Z and T. And there's a current that's flowing into the block along the wire. And that current is located at Z, the beginning of my block, and it's occurring at some time t. Okay. Now, back to the block itself. Because I'm separated by a wire, because I have two wires and they're separated, and by the way, these don't have to be wires, they can be planes, they can be more complicated geometries, but you know, there's two charged surfaces. So I'll have a capacitance between those charged surfaces. So I'll draw my capacitance, and this will be C dz. So C is a capacitance per unit length. And together they form a capacitance, a total capacitance of C prime. Okay. So the current's going to go in here, and the current's going to come out. And so the current at the end of the block, the end of dz, is going to be equal I of Z plus dz. And the voltage across this block here is also going to be voltage, and it's also going to be located in space at Z plus dz. Okay. Now, here's where circuit theory takes over for us. Okay? We pick dz to be so small that the time travel from that point to that point is negligible. Okay? The time travel from that point to that point is negligible. And so this is occurring at exactly that time in space as I have it here. Okay? That requires a little bit of thinking. That requires a little bit of thinking to get comfortable with that notion. The Z plus Z dz, that's cake, right? Because that's exactly how I set up the problem physically. But the time, at an instant of time, I've got a current and a voltage here and a current and a voltage here. Okay? The other thing that will drive you crazy when you try to relate this back to other parameterizations is we're interested in moving from the transmitter to the receiver. So we're going to pick our current flow to be down that axis there. Okay? I think if you do a lot of the transistor modeling, for example, or port modeling, so you'll have it's natural to have currents into both sides. But in the RF and in the transmission line world, that's not our business. Our business is to pump data or information, voltages and currents down this line. Okay, waveforms and signals down that line. Okay? All right. Now, the voltage across the inductor. Minus L di dt. And the L that I use is the L dz. If I look at the change in the voltage here to the change in the voltage there, not considering the inductor, just considering what I have here and here, then I have a term of the Taylor series. So these guys combine together. Del V del Z dz, and now I'll write my L prime as L dz, and that'll let me cancel my dz's here. And so I'm able to write a partial differential equation connecting V and I with a constant coefficient. The partial derivatives of dv dz, so left-hand side is a change in space, and the right-hand side is a change in time. Okay? Looks like to me it looks like a very, very, very watered down Maxwell's equation. All the beauty lost because of the simple one-dimensional geometry. But it is what it is. So now I have, now I'll consider the current across the capacitor. And the simple rule for capacitors, the change in the current is CD VDT. And the analog to this guy here is that it's also equal to del I del Z dz This is by just the geometry of the problem, or the Taylor series expansion. Same thing. And so I've put back in the dz. So now I can divide through by the dz. And I'm left with the second equation, which is a partial of I with respect to space. Balanced by a C dv dt on the other side. And again, that looks like the other main Maxwell's equations, horribly dumbed down. Okay. Which it should. These two equations are called the Telegrapher's equations. And that tells you where we are in history. Middle of the 1800s. Okay, so we're talking back in the days of Samuel Morse. And way back then. Okay.
What's the negative sign for the capacity equation?
I'm sorry, what?
The negative sign for the capacity equation.
Oh, I told you it would drive you crazy. It's the flow of the current. Yeah, it's you have to do the current balance, and I'm doing it in a funny manner. Okay. All right. Let's see. I think what I'll do. These are the equations that we want to solve, right? And there's a variety of ways that we're gonna manipulate them. But before we do that, what I'd like to do instead is give you a little bit more guidance on these lumped impedances. These lumped impedances, the capacitance per length and the inductance per length. Okay? And the way I'm going to do that is I'm just going to show you the equations, talk you through the equations for different geometries. Okay? So one of the transmission lines that you guys work with a lot are coaxial cables. Nice cylindrical coordinate system. Nice cylindrical symmetry. And these are the ones that the BNC cables that you've used, or the SMA cables that you've used for higher frequencies. And the way they're made, and I don't recommend you do this, but if you cut them in cross-sectionally, what you'll see is you'll see two metal conductors. Okay, the core metal conductor is a pin. It's a wire. It's a nice precision wire. And this is the little pin that if you look at the BNC connector, it's a little pin that's staring you in the center of that cylinder. And so when you slide that into to an oscilloscope or to a function generator, that little pin slides into a slot nicely to create a nice contact for the center conductor of this coaxial cable. Okay. Around the outside of it, you'll generally have a copper braid. And that copper braid gets connected, mechanically crimped, usually, not soldered, but usually mechanically crimped to the outside metal piece of that BNC connector. So as you lock that on to the outside of the housing, you create a nice fit and a nice electrical connection there. Okay. In between that, you'll have a polymer that's sort of a white, plasticky looking dielectric. Okay, and that dielectric will just surround the inner conductor and hold firm the connection between the inner and the outer conductor. We call the radius of the inner conductor A. That's a very small number. I'm going to guess it's about 1 millimeter or so. The outer conductor, the distance from the center of the geometry to the metal braid is B. Okay. And this cylindrical symmetry, if you might remember, we don't do this in this class, and it's okay, but you're going to be integrating a 1 over r, and with that 1 over r, you're going to get a logarithm, right? So you're going to have the inductance per length will have a log of the b over the a geometry factor. The material of the dielectric sits here in mu. And there's a 2 pi because whenever you have some sort of circle involved, you always have a pi. Okay? In fact, if you have a pi in your equation and you don't see the circle, you should look for the circle. It's very funny. It's very funny. There are a lot of problems where pi's pop in, and we don't necessarily see the geometry of the circle. I drop this pen on this desk, and I look at the orientation over, and the average distribution has a pi in it because the pen is free to rotate. Okay. So the things even though the pen is a line and this is a plane, there's usually a symmetry in there. So in this case it's a 2 pi. All right. The capacitance per length has the same log factor in it, B over A. And it's there's still a 2 pi in there, and then there's the material constant there. Okay. So the geometry, the fact that I've chosen a cylinder, gives me this factor here, and it gives me the 2 pi there. Okay? The choice of material, the choice of that polymer or that dielectric that I put in there, gives me mu and epsilon. It's funny if you think about it, most engineering problems are what material and what shape do I make that material out of? Okay, and that's what's in this formula. Nothing more. Okay. I also want to point out that a log is a very gentle function. For B over A, you're greater than 1. So log, you really have to stretch this log a lot. You have to make a big difference between B and A before you see much variation. So you're not going to get a huge range in this log of B over A. And for lossless dielectrics, you're not going to get a huge range in epsilon sub r. It's hard to get an order of magnitude. If you work really hard, you can get a couple orders of magnitude, but that's pretty. You have to work that way. So these are actually kind of tough constraints. You don't have a lot of leeway there. Okay. Now, I haven't said much about losses, but here are the formulas for losses. And the losses come into play in 2 ways in these problems. The first and most obvious way is that when current flows down these wires, there's going to be a resistance, a surface resistance, and you're going to drop your voltage across that resistor. Okay? So you add up the amount of wire that you have, the amount of surface that you have, and you have a 1 over A, you have an A from the inside here, and you have a B from the outside here. The circumference of those circles is 2 pi. And then you have a material resistivity of R sub S. And so when you add up the resistance to this and the resistance to this, you get an R is equal to RS over 2 pi, 1 over A plus 1 over B. You can rearrange that to your heart's content, but that's almost a literal kind of an additional, resistors in parallel. Okay. That's the obvious loss. There's a less obvious loss that goes on. And where that comes from is capacitors can be lossy. Okay? If you think about what's going on inside that capacitor, you've got a polymer, you've got a chain, and as you put a voltage across it, you're going to orient and reorient the electrons on that chain. Okay? That's what's going to be creating the capacitance at the AC frequencies, is the movement or the migration of electron clouds along the backbone of that polymer, so that it's polarized up and then polarized down. That's the very nature of what's going on inside that capacitor. Okay? And that leads to a lossy or a conductance between the internal and the outer and the external conductors of the coax. And that's found again with the log factor in here. And you'll see that I've expressed my loss term here as a real part of the epsilon and a complex part of and an imaginary part of the epsilon. Do you remember when I did K prime plus IK double prime to include loss? If you look back at what goes into K from the dispersion relations, that maps nicely to an epsilon prime and an epsilon double prime, and that's a very common notation in characterizing lossy dielectrics. Okay, a real part of the conductivity and a real part of the epsilon and imaginary part of the epsilon. Okay, so there are actually 4 circuit elements here, and in what we're doing so far is we're only taking into account the L and the C. But we'll go back and we'll put the loss in there as well. Now, let me talk about this G in a slightly different manner. Okay? Let me talk about this G in a slightly different manner. This is a fields and waves course. This is an electromagnetics course. And where there is voltage and current, and remember these are voltages and currents on boundaries that define a transmission line geometry. Right? So there's a voltage along this cylinder relative to this cylinder. And there's a current on one and a current on the other. So those voltages and currents are sources, they're boundary conditions. And so what they lead to is, and that's how we're going to track them. We're going to track what's going on the surface. But don't forget that in between them, in this white dielectric inside of our BNC cable, is a propagating electromagnetic wave. So there's actually a nice, simple electromagnetic wave that propagates in the annulus between the two conductors. And the conductors act to give it a boundary condition, both in terms of the current as a source and the voltage as either a driver or a coincidence. Okay, depending on chicken or the egg, whether you side with the chicken came first or the egg came first. Okay, so if that's the case, then there really is an E and an H in the white dielectric that's between the center conductor and the outer conductor. And if that's true, then we should fully expect a loss term from the E and the H that moves through a long distance, meters and meters, of the coaxial cable. Okay, in some cases, hundreds of meters. Does anyone know the typical distance of a cable TV hub feed? I think it's about 400 meters. Does that sound right? I think that's right. So if you have old-fashioned cable that runs into your house, that coaxial cable, the other end of that could be 400 meters away, 4 football fields away. Okay, I think that's true. I think that's a standard. I'm not real good with standards, but I think that is one. Okay. So so from these equations, we can kind of start to get a sense of the nature of the geometry, the nature of the parameters, where they're coming from, and so on. And I'm pretty much out of time. But what I'll do next time is I'll walk you through 2 other geometries, 2 wires. That's the twisted pairs that used to come into your house. How many of you have fiber into your house versus still DSL into your house? And you don't care because you just use your cell phone, right? Love it. And then we'll also do a parallel plate capacitance. Okay? All right.